Indeterminate forms and L'Hopital's rule, part 1. Suppose we want to find the limit as x goes to a, where a can be infinity, of f of x over g of x. And suppose that equals 0 over 0 or infinity over infinity plus or minus. Those are called indeterminate forms. Then L'Hopital's rule says that the limit as x goes to a of f over g equals the limit as x goes to a of f prime of x over g prime of x. This is not the quotient rule. Let's do just a few simple examples in this video. Let's start with one that we did way back when we did limits, before we even did derivatives. The limit as x goes to 0 of the sine x over x. Now if we plug in directly, we get 0 over 0. Since it's a limit, it's actually very close to 0 over very close to 0. But L'Hopital's rule says, since we have an indeterminate form, we can do the same limit, but of the derivatives of both the top, cosine of x, and the bottom, 1, and then plug in again, and we get the limit of the original. Let's take a look at another one that we did earlier when we were doing limits, way before derivatives. The limit as x goes to infinity of 4x squared plus 6x minus 2 over 1 minus x squared. Now, admittedly, there are simpler ways to do this problem, but I'm going to use L'Hopital's rule to show that it works. That is, I already know the answer is going to be negative 4 by doing highest powers top and bottom, but let's see what happens. So if I plug in infinity, we get infinity on the top and negative infinity on the bottom, because the highest powers will determine what happens, which means we can use L'Hopital's rule. So we'll do the limit as x goes to infinity of the derivative of the top, 8x plus 6, over the derivative of the bottom, negative 1 minus 2x. Now if we let x go to infinity, we get infinity on the top and negative infinity on the bottom, because the highest powers are what will determine what happens. But that just means we can do this again. In fact, we can keep using L'Hopital's rule after we plug in, if we keep getting an indeterminate form. So L'Hopital's rule says, let's do it another time. The limit as x goes to infinity of the derivative of this top, 8, over the derivative of this bottom, negative 2, and we get what we knew to be the answer. One more simple problem in a numeric format. So let g be twice continuously differentiable. Don't worry about this. This is just a technicality that will allow me to do the problem. Just saying g is a really, really nice, smooth function everywhere, because I'm not going to give you many points. In fact, I will only give you the following in this table. Let's say we have x, g of x, and g prime of x. And at x equals 0, g is 1, and g prime is 4. And we want to evaluate the following limit. Let's do the limit as x goes to 0 of e to the 3x minus g of x all over 2x. With the limit, of course, we plug in first. We get e to the 0, 1, minus g of 0, 1, over 2 times 0, 0. So our limit is going to 0 over 0, which is indeterminate. L'Hopital's rule says, let's go ahead and do this again, but we'll take the derivative of the top. So the derivative of e to the 3x is itself times the derivative of the power, so 3e to the 3x, minus g prime of x all over 2. And then we can plug in again. So now we get 3 times e to the 0, or 1, minus g prime of 0, or 4, over 2, which gives us a value of negative 1/2.